So let me recall again PMI. So if you remember, you call the given statement as P of n. Statement should be defined on natural numbers only. The first step is you show that the P of 1 is true. This is what you need to show. P of 1 must be true. Next step is your assumption. Assume that the P of k is true. This is your assumption for k belongs to n. And with the help of this, you show that the P of k plus 1 is true. This is a proving part, remember. You need to prove that the statement is true for n equals to k plus 1. This is your assumption, and this is again proving part. You show that the statement is true for n equals to 1. So once we do these two steps, the conclusion is the statement Pn, P of n, the statement must be true, statement is true. This is the concluding part for every n belongs to n, for every natural numbers. This is the concluding part from this two. This is what we did in 4 or 5 questions. With the same pattern, I'll do some more questions. So I'll be going now for question number 10 here. 10th question. Let me take that question as Pn here. P of n, Pn. That is 1 upon 2.5, sorry, 2 into 5, it's not 2.5, upon 1 plus 5 into 8, and so on. Last one is 3n minus 1 into 3n plus 2, that is equals to n upon 6n plus 4. You want to show this. This is a given statement. We want to prove this with the help of principle of mathematical induction. So what's the first step? For n equals to 1. Write LHS. What's LHS? Put n equals to 1. So if I put 1 here, this is 2. And if I put 1 here, this is 5. So this one alone, this much only. That is 1 upon 2 into 5, which is 1 upon 10. What about RHS? Put n equals to 1 here. So if I put 1 there, here 1 upon 6 plus 4, which is 1 upon 10. So you can say that here LHS is equals to RHS, and therefore P of 1 is true. You mean statement is true for n equals to 1. That's one thing. Now next part is our assumption. So we assume that P of k is true. This is our assumption part, where k belongs to n, any natural number. What is the meaning of this? As we wrote earlier in all examples, in the given statement, instead of n you write k. In the given statement, instead of n you write k. So I'm writing k here. In this statement, instead of n, I'm writing k. So 1 upon 2.5, 2 into 5, sorry, not 2.5, plus 1 upon 5 into 8, and so on, in place of nk here, remember. So 3k minus 1 into 3k plus 2 equals to k upon 6k plus 4. As you know, we always call this as equation number 1. Right? Up to this, you know, that's very basic and standard things. Now we go to k plus 1, P of k plus 1. So now most important part is we prove P of k plus 1 is true. We want to show this. What's the meaning of this? In the given statement here, instead of n you put k plus 1, and from LHS you get RHS. Okay, so I'm starting with LHS. You know, in fact, all these things. So LHS is 1 upon 2 into 5. And so on the last one, instead of n, I'm writing k plus 1, remember. So 3k plus 1 minus 1 into 3 into k plus 1 plus 2. This is what you have left hand side. Now what should be your RHS? Just for your information, you know procedure here. Your right hand side should be here in place of n. Here in place of n you must have k plus 1. So this should be your RHS. So right hand side should be k plus 1 upon here 6 into k plus 1 plus 4. This should be your RHS. So we write here RHS, and therefore we can say that in this statement, instead of n, if I put k plus 1 from LHS 2, we are getting RHS. And therefore I can say that the P of k plus 1 is true, and therefore I can write by principle of mathematical induction, PMI, Pn is true for every n. Pn means given statement is always true for all n belongs to n, for all natural numbers, remember. Okay, now this intermediate steps we need to write. So we fill these blanks. This we want to do now. This is the heart of the solution, remember. How we'll do? You know procedure. What we do? We write 1 upon 2.2 into 5 and so on. This is the last step. What's the simplification? Let me write here. So 3k plus 3 minus 1. So it's a 3k plus 2 plus 3 minus 1. What about this? 3k plus 3 plus 2 plus 5. And the previous term. This is the last term, remember. Now always, if you recall the previous solutions, we write here previous term. What's the previous term? Instead of k plus 1, you write k. So it is always this term, you know. So I'm writing 3k minus 1 into 3k plus 2. Right? Previous term, if you remember. Why we did this? Because you know this much. This much we know by equation 1. You know the value of this one by 1. Look at here. This much you know. That is k upon 6, k plus 4. So I'll place here. Instead of this, I'm writing here k upon 6k plus 4. This one as it is. Procedure is same in all questions, you know now. 3k plus 5. You know this is because of 1. Now you simplify this, you must get this, remember. So I'm simplifying. So what you can do is, you can see here, if you find 2 common here, then these 2 factors are same. So I'm taking this much common. 3k plus 2, I'm taking common. So what we'll get here? K upon here just 2 plus 1 upon 3k plus 5 here. Simplify this. I'm not doing this. If you simplify this much, you will get exactly this. Try this. This is simple algebra. So you have in this statement here, instead of n, you are getting k plus 1, right? You just do this. This is RHS, and therefore by PMI, Pn is true. That's one. Now let's go to one more question. Next question. Let me go for question number 11 here. So 11th number. Let me call that as Pn. So P of n is this 1 upon 1 into 2 into 3, 1 upon 2 into 3 into 4, and so on. The last term is here n into n plus 1 into n plus 2. You want to show that this is exactly nothing but n into n plus 3 upon 4 into n plus 1 into n plus 2. This is Pn. Now first part is we prove for n equals to 1. So for n equals to 1, left hand side. So it is just first term alone. You put n equals to 1, you will realize. So 1 upon 1 into 2 into 3, which is 1 by 6. What's RHS? Put n equals to 1. So 1 into 4, 3. So it becomes 4. Here 4 into 2 into 3. So it is again 1 by 6. So LHS equals to RHS. And therefore P of 1 is true. This is the first part. Okay. Next part is our assumption part. So now here we assume that the P of k is true. We assume that P of k is true. What is the meaning of this? That is, in the given statement, instead of n, you put k. So I'm doing that. 1 upon 1 into 2 into 3, and so on. K into k plus 1 into k plus 2 equals to k into k plus 3 upon 4 into k plus 1 into k plus 2. This is as we have called in all questions, that's 1. Okay. Now the most important part is the proving part. We prove that the P of k plus 1 is true. This is what we want to prove. We show that the P of k plus 1 is true, where k belongs to n always. Here everything comes from the natural numbers, remember. Okay, so what we do? We start with LHS. So left hand side. Instead of n, here we are going to write k plus 1, remember. So 1 upon 1 into 2 into 3. Here k plus 1, remember. So k into k plus 1 into k plus 1 plus 2. What I did? Just in the given statement, in place of n, I have placed k plus 1. Okay. Now, what we do? You know this. 1 into 2 into 3. The last term I'll keep as it is here. This is the last term. K. This is k plus 2. This is k plus 3. Here in this space, in this blank, what you are going to write? Previous term. Previous term means what? Here, instead of k plus 1, you just write, I think here, this is my mistake. This should be k plus 1. I'm sorry here. So now previous term. So instead of k plus 1, you just write k here. So I'm writing this one. You know it is always this term. So 1 upon k into k plus 1 into k plus 2. This is kth term. This is k plus 1th term. This is kth term and this is k plus 1th term. Remember, as we did in all questions. So now you know this much by 1. So I'll place that value. I'm going to put that value here. So what is that by 1? This much. So it is k into k plus 3 upon 4 into k plus 1 into k plus 2 here, plus this one as it is, 1 upon, here it should be k plus 1, remember this was my mistake. So k plus 1 into k plus 2 into k plus 3. From where we could write this? By 1. So I'll write by 1. Now we simplify this. Remember, what you want on the RHS, that should be there in your mind. What you want on the right hand side? here in place of n you should have k plus 1 everywhere. K plus 1, k plus 1, k plus 1, k plus 1. That's what you want, remember. Keep that much in your mind, remember. Okay. So now the question is just simple algebra here, nothing more than that. But what you want, that should be in your mind. What you want, let me write here. I'm writing here in the last step. So I want k plus 1, k plus 1 plus 3, k plus 4 upon 4 as it is, k plus 1, so k plus 2, here k plus 1, so k plus 3, remember. This is what I want, this is RHS. So we just simplify this and we try to get this. It has to be this one. If it is not this, that means some algebraic mistake must be there. So we try this. So just simplify, you will find k plus 1 this much common, so I'll take that much outside. K plus 1, k plus 2 I'll find outside. What will get inside the bracket? K into k plus 3 by 4 plus 1 upon k plus 3. Okay. So let me simplify here. K plus 1 into k plus 2. Here you have whole square. So k into k plus 3 whole square plus 4 upon 4 into k plus 3. Okay. So now here, if I simplify, 1 upon k plus 1 into k plus 2. What about this? This would be quadratic and I'll take k inside. So it would be k square and then k. So k cube plus 6k square. Actually middle term is 6k. So 6k square plus 9k plus 4. You will get this cubic into 4 into k plus 3. So here now factorization of this one, which you can try in rough. It would be k plus 1 into k plus 1 into k plus 4. You can just try upon this expression 4 into k plus 1 into k plus 2 into k plus 3. So 1 k plus 1 will get cancelled. So you are left with this thing by 4, that is this, you can see. So therefore P of k plus 1 is true, and therefore by PMI Pn is true for all n. By PMI Pn means given statement is true, always true, remember. So I'm a question number 12 now. Let's take Pn, the given statement, as a plus a into r plus ar square and so on, a into r raised to n minus 1 equals to a into r raised to n minus 1 upon r minus 1. This is a given statement. Okay, so first we prove for n equals to 1 here. So for n equals to 1, left hand side here, LHS, put 1 here. So r raised to 0, that is 1. So just a, that means this much only. Go to right hand side. What is RHS? Put 1 here. So a into r raised to 1 minus 1 upon r minus 1. So this will get cancelled. This is a. So therefore LHS equals to RHS, and therefore P of 1 is true. This is the first part. Okay. Now we go to assumption part. We assume that this is our assumption part. We assume that the P of K is true. What is the meaning of this? That I am writing. That is, in the given statement, instead of n you put k. So we have this a plus ar plus ar square and so on. A into r raised to k minus 1 equals to a into r raised to k minus 1 upon r minus 1. We call this as 1. Okay. Next part, we're proving part. We prove, this is the most important part, we prove P of k plus 1 is true. This is what we want to prove, remember. Proving part. So, I'll start with LHS here. Instead of n, we put k plus 1. We get this, but instead of n, you must have k plus 1. So, I'm writing LHS. What is LHS? A into AR square, and so on. A into r raised to, here k plus 1, remember. K plus 1 minus 1. Okay. What you did, just here instead of n you have placed k plus 1. Now we write always as we did previous term. Now here this is a last term. Last term is a into 1 will get cancelled, r raised to k. What's the previous term? It is always this, 1 less power. So a into r raised to k minus 1. Now why we did? Because you know this much by equation 1. Here is equation 1. You see this much, that's 1. So I'll place the value of this one. So if I place the value of this much, what will get? A into, I'm just writing by 1, remember, r raised to k minus 1 upon r minus 1. This one as it is, a into r raised to k. This is by 1. What you want on the right hand side, that should be in your mind, remember. We want this much. In this formula, instead of n, you must have k plus 1, remember. Remaining things are that is. So we want this a into r raised to k plus 1 minus 1 upon r minus 1. This should be there on the right hand side. That should be there in your mind clearly. You want this much, remember. Okay, so we just simplify and we try to get this, or we must get this at the end. This is now simple algebra, remember. So I'm just simplifying. What you can do is, you can find a common and r minus 1 as the LCM. So here r raised to k minus 1 multiplying with this. So r raised to k into r minus 1. The whole upon r minus 1. What I did, taking a common and this r minus 1 as the LCM. So now further, a into, if I open the bracket, r raised to k minus 1, here r raised to k plus 1, bases are same, so you can add the exponent, minus r raised to k upon r minus 1. So this will get cancelled. So what we are getting? R raised to k plus 1 minus 1 upon r minus 1. This is what you wanted. You see on the RHS, as I wrote there, this much you wanted. So in the statement here, instead of n, you are getting k plus 1. Just to compare, you will realize. Okay, so this is your RHS here, and therefore I can write P of k plus 1 is true, and therefore by PMI, principle of mathematical induction, PN means given statement is always true, for all n belongs to n. So given statement is always true. Okay. Now question number here 19 to 23, all are divisibility questions. These are the based on divisibility. So we'll see. If I do 1, you will realize. So I'll go to 19 first. For all this question, procedure is same, remember. So what's the statement here? P of n. The statement is this. We don't have here like RHS and LHS and so on. N into n plus 1 into n plus 5 is a multiple of 3. Multiple of 3. This expression n into n plus 1 into n plus 5 is a multiple of 3. So we prove this using PMI. We want to show that this is always true for every natural number. Okay, so what's the procedure? For n equals to 1. Put n is equal to 1. So 1 into 2, here 6. So 12, you know, is a multiple of 3. 12 is a multiple of 3. Multiple of 3 means divisible by 3. And therefore, what's the conclusion? P of 1 is true. This is always true. P of 1 is true. Now our assumption. What is our assumption part? We assume that P of k is true. We assume that the P of k is true. That is, in this statement, instead of n, if I write k, which is also multiple of 3, that is k into k plus 1 into k plus 5 is a multiple of 3. Multiple of 3 means what? You can write like this. Therefore, you can write k into k plus 1 into k plus 5 equals to multiple of 3 means this may be 3, 6, 9 and so on. So I can write 3m for some m belongs to n. I hope this is clear to call this as 1. Multiple of 3 means what? It may be 3, 6, 9, 12. So you can write in general 3m, remember. So we go for now proving part. We prove that P of k plus 1 is true. This is what we want to show now. That means here instead of n, if I put k plus 1, then which is also multiple of 3. Okay. So I'll start with this. K plus 1 into k plus 1 plus 1 into k plus 1 plus 5. What I did, I have just written instead of n, k plus 1. Here k plus 1, k plus 1, k plus 1. Okay. We just simplify this. We use equation 1 and we'll show that this expression is also multiple of 3. Okay, so this is, let me write k plus 1 into k plus 2 into k plus 6. 5 plus 1. Okay, I'll just express as a polynomial. So this is k square, 6k plus 2k, 8k plus here 12. Now one more time I'll open here. So k cube, 8k square plus 12k plus k square, 1 into this, 1 into this and 1 into this, plus 8k plus 12. So here k cube, 8 plus 1, 9k square, 12 in plus 8, 20k plus 12. Now we have not used this one. One need to be used, remember, always, you know, like previous question. So what I'll do, I'll simplify this and I'll put the value of some expression. So now let me write here by 1. If I open this, this is k square, so k cube. This is 5k plus 1, 6k and plus 1, so 6k square. 5k plus 1, 6k, so 6k square. and here plus 5, so 5k equals to 3m. Now what you can do is you can put the value of at least k cube. I'll put the value of this one. So what's the value of k cube from this? It is 3m minus 6k squared minus 5k, and this one as it is. That's plus 9k squared plus 20k plus 12. Fine. What I did, just I placed the value of k cube. What is that? That is 3m minus 6k square minus 5k, and this one as it is. Now let's simplify this and this, so plus 3k square, this and this, it would be 20 minus 5, so 15k, and plus 12. You can see that here you will find 3 common, so m square plus k square plus 5k plus 4. Now you can consider this is like one constant, whatever it is. It may be 1, 2, 3, 4, so you can call the 3m dash, where m dash is again a natural number, remember. So see, look at here, you have shown that everywhere you have equals to 3m dash. Therefore you can say that this is multiple of 3, and therefore p of k plus 1 is true. And therefore by PMI, Pn is true for each n, for all n belongs to n. What's the meaning of this? Pn is true. That means given statement is always true. That means this number is always multiple of 3. You take any value of n, you can take 1, 2, 3, 4, 100. You will see that this number is always multiple of 3. So that's what we have shown. 1 is used effectively, remember here. Now, sometimes, normally what students do, they find the value of k plus 1 like this here. Suppose if you have here k plus 1, so you cannot put like this. This is wrong, remember. If I put k plus 1 equals to 3m upon k into k plus 5, this way 1 should not be used, remember. Always you express like polynomial and put the value of one part. You will get the required thing, remember. Don't do like this. (22) question number. Your statement Pn is here 3 raised to 2n plus 2 minus 8n minus 9 is divisible by 8. It means indirectly this is a multiple of 8. Procedure is same like previous question. There multiple word is used, your divisibility word is used. So for n equals to 1, let's see, put 1 here. So 3 raised to, if I put 1, this is 3 raised to 4 minus 8 minus 9. So this is nothing but the 81 minus 17. So it would be here 64 is divisible by 8, is divisible by 8. Okay, so therefore p of 1 is true here. Fine, we go for now assumption part. So what's the assumption part? We assume that p of k is true. What is the meaning of this? That is, instead of n, you put k in the statement. So therefore 3 raised to 2k plus 2 minus 8k minus 9 is divisible by 8. So you can say that this is a multiple of 8. So I can write 3 raised to 2k plus 2 minus 8k minus 9 equals to 8m. Divisible by 8 means multiple of 8, where m belongs to n. This must be like 8 or 64 and so on. That is multiple of 8. We call this as equation number 1, and we'll use this in the proof of k plus 1, you know. So now we prove p of k plus 1 is true. So what we do here in this statement, instead of n we put k plus 1. So we have 3 raised to 2 into k plus 1 plus 2 minus 8 into k plus 1 minus 9. So we simplify this and we'll show that this is multiple of 8 like this. So here 3 raised to 2k plus 2 plus 2, so plus 4 minus 8k minus 8 minus 9, so minus 17 here. Now we need to use the equation number 1. So what I'll do here, I'll put the value of this much. So I'll rewrite in this form 3 raised to 2k plus 2 into 3 raised to 2. Both the bases are same, so you can add exponents, so you'll get exactly this minus 8k minus 17. Now I'll put the value of this much by 1. I hope this is clear to you. Or let me write here what I did. 3 raised to 2k plus 4, I wrote like this, 3 raised to 2k plus 2 plus 2, and which you can write as 3 raised to 2k plus 2 into 3 raised to 2. Why I did like this? Because I have 1 in my mind, remember, I need this much. So 3 square as it is, that is 9 as it is. So by 1, what you will get? Your 8m, this 2 on the other side, plus 8k plus 9 into this 9 as it is, minus 8k minus 17. I'll write just by 1 here. This is because of 1. Value of this expression, this much. Now we simplify and we'll see that this must be multiple of 8. You must have 8 common here. So here 72m plus what is this? Again 72k plus 81 minus 8k minus 17. So 72, this is 64, and this is again 64. So you can take here 8 common. So 9m plus 8k plus 8. You can call this as m dash. So 8 into m dash, where m dash is this 9m plus 8k plus 8, which is a natural number, whatever it is, but it would be an integer. Okay, so therefore what you have shown, this expression when I put n equals to k plus 1 is a multiple of 8. So therefore p of k plus 1 is true, and therefore by PMI, Pn means given statement, Pn is true for all n belongs to n. That means Pn is true for all n belongs to n means this number, you choose any n here, this number is always divisible by 8.